Action. Yeah, got it. Sorry. Sorry, I'm not familiar with that. Anyway, let's do it this way. Um, okay, we have 4 parts in this talk. First, an introduction, and then we talk about the proposed adaptive utilization scheme. And then we have some experimental demonstration of the scheme and a final summary. First, let's look at the motivation. Mainly, the target of this work is to have a combined uh, adaptive equalization scheme and a sequence detection, which we use MLC here. And so we can deal with some very severe ISI problem. Because we had previous work when I was at Tyco, we did some MLC stuff for a narrow filtered signal to get high spectral efficiency transmission. At that time, the pattern dependency was only utilized by the MLC part. And there was some problem in the adaptive equalization, which was not resolved. As I will show you, it's basically the ISI pattern dependency is a feature we want to utilize. However, the 2 modules in a receiver, coherent receiver, adaptive equalization and MLC, because the equalizer do the job first, and it can just destroy all the ISI or most of the ISI feature the MLC want to have to do its job. So then we think maybe we can do the job. I can make the 2 work together so they don't compete with each other, but with the combination, they can work together. So that's the motivation. Specifically, the ISI in a optical communication system, there's a dynamic signal distortion, which is dynamic, may not be ISI, but like polarization state rotating. And also there's ISI like PMD induced ISI. There's also narrow filtering induced ISI, which is highly pattern dependent. Like I said, the adaptive equalizer was introduced to deal with the dynamic distortion, including dynamic ISI. And we did MLC to deal with the pattern-dependent ISI. And those 2 cannot be, they are not necessarily replaceable by each other when they face the entangled ISI problem. So then we just imagine maybe we can have the adaptive equalizer to be able to distinguish some target pattern-dependent ISI, so it doesn't touch it, doesn't shoot at it, and just leave it to the subsequent MLC to do its job. That's the motivation. And then our goal here is we want to have this adaptive equalizer, which we call it adaptive pattern-dependent equalization, PDE, to distinguish some preset pattern-dependent ISI. Here in this talk, it's mainly just narrow filtering induced ISI. And once it can distinguish this part, then it can just avoid to destroy it. It just compensate only ISIs other than the target. And then the target will be left to the subsequent MLC. Why let MLC do this? Because in theory, MLC is the optimal solution for ISI because it has a nonlinear process. And adaptive equalization still has a filtering structure. This kind of structure is not optimal for ISI mitigation. And then with that, we also want to show with experiments and not just simulation, right? To show the concept does work. Now let's look at the structure of a transmission system with the proposed scheme. In the on the receiver side, you can see those blue modules are the modules involved in this scheme. We have adaptive equalizer here. We have MLC there. So like I said, we want to combine those two, let them work together. And the link or the bridge between them are these two modules. One, the major one, the pattern-dependent ISI lookup table. And together table, we have a lookup table training processor. And with the four things work together, you can see actually this lookup table link those two modules together so that they have some shared knowledge of the ISI feature, and then they can work with each other. And to show the difference of this scheme with a traditional or conventional scheme, this is for illustration only. I add one switch here to have, when it's on, it's a proposed scheme. The pattern-dependent lookup table feed the information to adaptive equalizer. You can also just switch it off, then the scheme will become a regular equalizer scheme. And here we want to show the pattern-dependent ISI features, how this proposed scheme can distinguish the feature and leave the ISI feature target one to the MLC. On the transmitter side, we do a narrow filtering. Then we get, this is basically our base constellation is a QPSK constellation. And once you do a very narrow filtering, the 4-spot QPSK will look like this, becomes a like 36 spot. It's more like a QAM, but it's not really QAM because this, when you talk about the QAM, you're talking about symbol by symbol detection. So you get a constellation based on one symbol sampling. But here we have, again, we still have one symbol sampling, but this structure in the constellation comes from not single symbol modulation, but from multi-symbol ISI. So it's important to understand that. And so this is the transmitter side. And then on the receiver side, like I said, I want to show you, if we have this switch off, this guy for QPSK, it will work like a regular CMA equalizer. It will try to give you a nice 4-spot QPSK constellation like this. And but once you have this, like I said, it may look good for a QPSK target, but when you transfer this, when you hand this to the MLC, then the MLC wouldn't be able to do its job because it would expect something like that because it tells you there is an ISI feature for you to deal with, and the adaptive equalizer just destroyed all the fancy thing he can play with or it can play with. In that case, if we put the switch on, and then the adaptive equalizer will know also have this target feature, right? The lookup table will have all the information here. And then the adaptive equalizer will target at this, try to do its job for all the dynamic tracking, like polarization tracking, or PMD compensation, residual CD compensation, all the job, but just leave the part we want untouched or mostly untouched by doing that. And In this way, you can see here we can achieve this by switching this switch on, and then after this, after the frequency offset compensation, base compensation or estimation, we have this feature kept for the MLC. And basically, I try to, I probably repeat this many times. It's just the idea is the adaptive equalizer is guided by a lookup table, which also guide the MLC. So you have one guidance for the two modules, so they can cooperate with each other. This is the experimental setup for this demonstration. In this, we have on the transmitter side, we have a narrow line with ECL, and we have a 35 gigahertz bandwidth DAC with 120 gigasample per second sampling rate. And we also have the balance 67 gigahertz, 4 of them for the signal components. And also we have a 4-channel integrated 60 gigabaud linear driver and an optical modulator with 50 gigahertz bandwidth. And the VOA here and EDFA is just for noise loading. This is a back-to-back measurement demonstration. This is a concept proof. So we started with back-to-back experiments. And on the receiver side, we also have this 100 kilohertz ECL laser. And we have this integrated coherent receiver, which is 70 gigahertz with 70 gigahertz balanced photo detector. And the EDFA here added is just because we didn't have a TIA in this experimental setup, and we want to have some gain on our signal. So we use a EDFA so we can make our local oscillator amplified a little bit so that we can boost up our received signal. And well, of course, this is the offline DSP for this experiment data processing. Here is the eye diagrams in the experiment, also calculated at the transmitter side. Because this experiment, the ISI, target ISI, comes from pre-DAC narrow filtering. So why would you do that? Because one application you can think about is usually these days you want to go to very high baud rate, and your DAC mainly most of them will be bandwidth limited. You never have enough bandwidth from the DAC or ADC, and the DAC is more the constraining here. And our scheme would be able to help in that sense because you can, before DAC, I have a QPSK signal 60 gigabaud. The bandwidth without filtering, the bandwidth would be pretty high. And now if I do a filtering digitally before the DAC, then my signal will have a large or high baud rate, but the bandwidth will be limited. Of course, that will introduce ISI. This is the basic idea. I have ISI, but the bandwidth will be narrower, and the DAC can do its job. And the ISI will be compensated at the receiver side. So I don't have to go to high order modulation. Like if I do symbol by symbol detection, I can go from QPSK to 16 QAM, 64 QAM, but all just one symbol, right? Here, I have a base QPSK, and I have